Let's pray. We'll get started. Father, thank you for this day and the souls who are here, Lord, to learn. Pray that you would help me to just be clear, give us good understanding of these things and good recall later on when we need them, whether it's for tests in this class or for other things that they may go on and do with their education or with their careers. Father, may this all be done for your glory and for our good. We pray in Jesus' name. Amen. All right. Well, last time we were looking at valence electron shell repulsion theory, right? And so we've looked at some shapes and things like that. Just want to do a little bit of review, okay?
Okay.
So if I have, let me go back, let me not just, I got something like that, or like this. This. Let's go here. Finally here. What shape is this? Linear. This one? Try to do it without your nose. And this is what you got to be able to do on a test.
Okay.
Right? This one?
Tetrahedral.
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 This one?
Something planar.
No, not
No,
here.
Pyramidal something.
By trigonal pyramid.
Trigonal bipyramidal.
Oh.
Okay.
Pyramid.
Alright. Good. And this one? Octahedral. Okay. Alright, so essentially if I've got two domains, electron domains, in this case both bonds, right? Linear. I mean, this one's easy, this one's easy. These are in a plane, right? Two pyramids, so this is trigonal, bipyramidal. And then finally over here, octahedral, so something with 8 faces on it. Then we can start taking stuff away, right? So if I take this same thing, same general premise, but now I'm going to have unbonded, or yeah, I'm going to have non-bonding electrons, right? So I've got electron pairs. Well then I could have something like this. They do it like this. I better go ahead and just stay with their nomenclature. It's in the book. Disappear. So in this case, you don't count these, right? We're looking at this one. We're looking at everything. This one we're now only looking at where I've actually got atoms, right? So we don't count this one. So it's not trigonal pyramidal anymore or planar anymore. What is this one?
Bent.
This one's bent. Okay. This one would be. What is this one going to be? Did we do this one the other day? It was tetrahedral, right? But now we're going to take this out. So what shape's left?
Trigonal pyramid.
This would be trigonal pyramidal. Good. I don't know that we covered that one. But essentially it's, if you were to look at it from the top, at it from the bottom. It's easier to draw, right? So it's gonna come in like this. So you form a pyramid. Well, that works from the top too, doesn't it? You get this kind of idea. I got 3 faces of a pyramid. Okay. Then we come over here and we'll do, actually we could do this one with only 2 pairs. So it's the same thing, but now I've got unbonded electrons here, and I've got unbonded electrons here. So I've only got this and this, right? So now this is actually my only shape. What shape is that? The same as this. It's going to be bent. Good. All right. And then we come over to this one, and we know that this is trigonal pyramid, bipyramidal. But if we start taking one of them out, what shape is that?
Saw.
Seesaw. Seesaw. All right. See it?
Now I see the seesaw.
Okay. Good. It's you'd have to have it like up on these 2 things elevated with these going out, and then they kind of
Like,
yeah. Okay, that's with 1 pair gone. With 2 pairs gone, this way. What shape is this going to be?
It's the T.
Just a T. They're all in the same plane. Okay, and then we can go 1 more. Now all I've got with these, what shape is that?
It's the quadratic one or something.
Not on this one. It's just
Linear.
these are your only
Oh,
element.
linear.
Yeah, so it's going to be linear. Good.
And this one with.
Okay. Now, octahedral, right? 6 bonds, right? 1, 2, 3, yeah. Okay. So now we come over here, and this one has a lot to it. Okay. This one is a square pyramid. How are we getting that? We've got 1, 2, 3, 4.
But with the electrons, it's a square pyramid. Without, it's a triangle pyramid. If I'm not wrong.
This is octahedral.
Okay.
This one is square pyramidal. Be real honest with you, I'm never going to give you this one. You'll be okay. Let's do this next one. Okay, so I've got my center one, I've got unpaired electrons up here, I've got that all these are here. What shape is that?
A square planar or something?
Square planar. These are all on the same plane, right? You got essentially you got 2 axes. You got these on one axis, and these are all at another axis going around it 90 degrees. Okay, so that's square planar. All right, now 2 more to do. And we're done with this. So I've only got electrons or atoms here, 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 and here. These are in a line, right? And this is coming off. What shape is this?
Yes. Do you know plan?
Well, you got this here, right? And then you got another one that's coming off. The way that we've drawn it might look like it's an angle, but remember this is this plane and this plane are 90 degrees from each other.
T.
So it's a T.
Okay.
All right. And then our last one over here. Yeah, the rest of these, it's as though they're not there, right? So what shape will this be? You have none in this plane, your only electrons are in this plane.
Linear.
Pardon?
Linear.
Linear. Good. Why is it that in these shapes, why do these want to be here?
Because you need the most space for the
Most space, right? And so that allows that to happen. All right. Well, is there anything else out of that that we're going to do? Good. We're going to move on to molecular orbital theory. So draw a line, give it a new title, molecular orbital theory. So this is chapter 8 in the book, okay? And we're going to begin with valence bond theory, which allows us to springboard into molecular orbital theory. Okay, so valence bond theory, it says here, describes a covalent bond as an overlap of half-filled atomic orbitals. So let's think about hydrogen, right? Hydrogen, its electrons are in which orbital? 1s, right? How many electrons are in the 1s? 1. 1s1, right? So if I've got hydrogen here, it's 1s1. I got a hydrogen here, it's 1s1. Each of them has how many electrons in that 1s orbital? Say 1, right? So I can draw my nucleus, and here's my electron cloud, or here's my orbital, okay? So, what we're calling valence bond theory says that a bond, a covalent bond, is when these half-filled orbitals overlap. Okay? So what I would need to see happen to call it a bond is I need this to slightly overlap. Right? And so this region where they overlap is a bond. It's a covalent bond. Of course, it's a pair. It's now a pair of electrons shared between two bonded atoms. We say that orbitals on two different atoms overlap when a portion of one orbital and a portion of a second orbital occupy the same region. That's what we're showing here with this blacked out area. According to valence bond theory, a covalent bond results when two conditions are met. Number one, an orbital on one atom overlaps an orbital on the second atom. That's what we're drawing here. And two, the single electrons in each orbital combine to form an electron pair. The mutual attraction between the negatively charged electron pair and the two atoms' positively charged nuclei serves to physically link the two atoms through a force we define as a covalent bond. So essentially, there is an attraction here between the electron here and this, and the electron here and this, right? Let me read that part again. This, negatively charged electron pair and the atom's positively charged nuclei serves to physically link the two atoms through a force we define as a covalent bond. The strength of a covalent bond depends on the extent of overlap of the orbitals involved. So the more they overlap, not all covalent bonds are the same. Some are going to overlap a little, some are going to overlap a lot. The more they overlap, the more we expect that, the stronger we expect that bond to form. How will you know if it overlaps a lot or a little? How will that manifest itself?
Electronegativity.
Yeah. How are you going to measure this? Whether it's a strong bond or a weak bond, whether it overlaps a little or it overlaps a lot?
The capacity to have to react with other stuff.
That is one way, definitely, by reactivity, or the lack of reactivity. But another way to actually physically measure is to look at bond length.
Okay.
The more they overlap, the closer those nuclei will be. And the less they overlap, the further away they'll be. Okay? So it can be measured in terms of bond length, which is really, really important coming up. I'll show you that in a minute. It says the energy of the system depends on how much the orbitals overlap. There's a figure, blah, blah, blah. Okay. The optimum distance between two bonded nuclei is the bond distance between the two atoms. Optimum distance between the... They didn't write that well. Here's the deal. You got a couple forces at play, okay? We've got positively charged nuclei, and we have negatively charged electrons, right? Okay? These two are attracted. That's why the electron stays put and goes around it. I bring in another atom, right? I got the same two factors. But now when I bring them into each other, I've got other factors, right? What's true of this electron and this proton?
Attract each other.
They're attracted, right? So between my protons and my electrons, I have an attraction. Great. I got two other forces at play here, though, right? What are they?
The repulsion from the proton.
Yeah, I've got a proton and a proton, which equals repulsion. And I've got electron and electron, and that is repulsion. Well, if repulsion were on, right? So attraction must be greater than repulsion. These two near each other, right? This is going to increase. It's a function. It functions on an inverse square law, right? So as these come together, these two increase, and these two increase. But this increases at a greater rate than this one does because it's a stronger force. To a certain point, how close can I get these two things? Comfortably, right? That's the thing. they're attracted to each other at a distance. As you get closer, the attraction is greater. It's like two magnets, right? At first you have them real far away, you don't feel it, but then you get it real close and you actually have to pull them back. They want to snap together, right? Okay. Opposite is also true with the repulsion. You flip those poles, and at first there's not a problem, but eventually I've got to actually physically push them, and if I get them real close, they will spring apart. There's some point at which, I can have them, I can just leave them on a desk and they're just going to hang out. It's not a problem. Anything closer, they physically want to. And same thing, I can reverse that, and at some point they'll just hang out, but then eventually if I get, they'll snap together without me doing a thing about it. I've got these two factors at play, the repulsion and the attraction. There's an optimal point at which everything's in equilibrium, okay? And so it's the amount of attraction and the amount of repulsion are equal, and so this thing stays put. If I wanted to get them any closer, I've got to seriously overcome repulsion. If I wanted to get them further away, I've got to seriously overcome attraction. And this is the optimal bond length. Having said all that, let me read this again, and then we're going to draw some stuff, okay? So the optimum distance between the two bonded nuclei is the bond distance between the two atoms. Great. The bond is stable because at this point the attractive and repulsive forces combine to create the lowest possible energy configurations. If the distance between the nuclei were to decrease further, the repulsions between the nuclei and the repulsions of electrons are confined in closer proximity to each other. They become stronger than the attractive forces. The energy of this system would then rise, making the system unstable. Okay, so they give us this really great diagram. It really is. It's very good for understanding all this. Okay, this is our energy in joules. And this is our distance between nuclei. Okay. Somewhere over here, I've got two atoms. They've got some kind of distance x between them, okay? And whatever energy this is where they're not forming a bond, they're not close enough for any of these forces to have it. Whatever this is going to be our set energy, okay? We're going to call this 0. No energy involved, okay? Now, as they get closer and they want to form a bond, they're going to become more stable. These attractive forces are going to draw them together, they're going to hold them together. I don't have to add energy to the system to make them bond. In fact, they'll actually release energy. And if I want to break the bond, I'd have to add energy to pull them back out. Okay? So the energy of the bond formation, if it's spontaneous, which this one's going to be, is actually going to be negative, right? Any spontaneous reaction always has a negative energy, right? So I'm going to have some point over here where I'm in a stable bond between these two things, right? We're overlapping, okay? And this is going to be my negative energy, right? So for hydrogen, this is actually calculated as negative 7.24 times 10 to the 19th joule per molecule, okay? Not a lot of energy, but we're only talking about one molecule. So if I wanted to liberate 2 hydrogen ions, this is how much energy I'd have to have. If I took 2 hydrogens, 2 molecules. If I wanted 2 hydrogen molecules and I put them in a closed system and got them near each other, I would expect that this is the amount of energy that any 2 would release. It would heat up by that amount every time that they combine. Talk to me.
No, it's okay.
Okay. Yes, sir.
What would be required for you to push them close together?
Yeah,
More energy?
we're gonna get there in just a second. That's a good question, right? So if this is non-bonding, right, and this is optimal bond length, right? lowest possible energy state. This is the most stable. Then my graph is typically going to look like something like this, okay? We're going to, as these two things get closer, in other words, they're going to release energy, okay? But now, actually I should have drawn it, well, it'll be okay. Remember, this is my bond distance, so this is far away, this is close, so I'm just going to make a note. This is like really close. This is far away. Okay? Now, if I want to get them closer, so I'm pushing them closer. Now at this point I'm going to have to overcome my repulsive forces with added energy because the attraction is not sufficient. I've got to start adding energy to this thing quickly, right? Well, what's going to happen to my line here that's doing energy versus distance?
It's gonna go up.
What's that shape going to be?
A line?
It's going to be like exponential, right? I mean, or trigonometric, whatever word I'm trying to, I mean, it's going to do something like that. Okay, it's going to be rapid. They will I mean, it takes nothing. These guys will spontaneously form to this point, but to get them any closer, you have to add energy, and you literally can't add enough. Well, you can in a sun if you're doing thermonuclear reactions, get them close enough that they would fuse. You know, that's the proton-proton chain from astronomy. And you've got to have something on the order of 12 million degrees Kelvin to make that happen. So you and I can't just do this, which is why this thing just goes off the charts, right? Okay. So what's a bond length going to be? What this is showing us, and there's a graph like this for any two atoms that are forming a molecule, is whatever their lowest energy state is, that's the bond length. Okay? All right. So it says here the bond energy is the difference between the energy minimum, that's here, which occurs at the bond distance, and the energy of the two. Oh, I'm sorry. This is the energy minimum. The energy of the distance at which they bond, and the energy at which they separate. So this distance here, I need a color. Do this in black and white. This distance, I'm going to do it here, okay? This is the bond energy. Alright? Makes sense? You need to know that. If I give you something like this and I give you real numbers, you got to tell me what the bond energy is, right? So,
How you say it again? Low energy?
this is the low energy, right? This is when it's stable, this is its minimum. And this is when it's not bonding at all.
Okay.
Okay? And so we define E as when it's, or 0 as when it's not bonding at all. And this is the amount of energy that's released when it's at its optimal distance. This Y value is between these two, that's my bond energy. Right? It's fairly intuitive. Yeah, not going to spend too much more time on that. So, what gives you a number of bond lengths? Not too worried about that. It's easy enough to go look at. There's a difference between the energies in double bonds and in single bonds.
Yeah.
Okay. Rule number 1, all single bonds are sigma bonds. Greek letter sigma. It's like an O with a little curly coming off. It's an S sound in Greek, and sigma. All right. All single bonds are sigma bonds. That alone does not help you that much to understand what a sigma bond is. Okay. I want you to think about our molecular geometry. So an s orbital has a spherical shape, right? But a p orbital, you have 3 p orbitals, right? And so one of those p orbitals is in this plane. One of those orbitals is in this plane. And one of those orbitals is in this plane. Right? Okay. And of course the shapes of these, they're actually dumbbell shaped, right? So it's like this. So there's one. There's 2. Here's 3. Of course we fix this slightly. So you can see how I've got them. I've got 3 sets here, right? 1 going vertical and 2 here in this plane. These are your P's. Okay. So the thing about a sigma bond is the sigma bonds always happen linearly between 2 nuclei. So I can have an S bonded with an S, and a sigma bond will keep these 2 nuclei in the same plane. It will occur between, the bond itself will occur in plane with these, okay? I can do a sigma, or I can do an S with a P. I should have drawn that better. And it keeps these. Okay. I can do this with 2 P's. And this will keep these in a plane. Okay. So an S sigma bond will always keep your nuclei in the same plane. Always. You read what this says for you. The overlap of 2 s orbitals, as in H2, the overlap of an s orbital and a p orbital, and the end-to-end orbital overlap of 2 p orbitals, such as in Cl2, all produce sigma bonds. A sigma bond is a covalent bond in which the electron density is concentrated in the region along the internuclear axis. So this is what we have shown. I didn't say it quite the same way, but it keeps the concentration of electron activity between the 2 nuclei. That will not be true of pi bonds. That is, the line between the nuclei would pass through the center of the overlap region. We see that in all 3 of those. Single bonds in Lewis structures are described as sigma bonds in valence bond theory. Okay? So all single bonds are sigma bonds. A pi bond is a type of covalent bond that results from side-by-side overlap of 2 p orbitals. Okay? I'm going to race over here and start drawing this. And we'll have videos and stuff because this, I won't be able to draw all that's going on. It gets too crazy. All right. So let me read this. This is now pi bond. So this was a sigma. We're using Greek letters for these, and this is the Greek symbol pi. You're familiar with that from math, if not from Greek or something. So pi bonds. A pi bond is a type of covalent bond that results from side-by-side overlap of two p orbitals. So what does that mean? Here, I've got two p's that are in the plane here, right? But now, what if I've got two that are if I've got a bond here already between two atoms, okay? Well, now I can't put another one in this plane, right? Just look. If I've got this and I got another one of these and they're overlapping right here, that's great. But if they're going to have other bonds, I've got to do it either with these reds or I've got to do it with these blues. Sylvia, I want to make sure you see this, okay? If I had another one of these molecules, exactly, and I wish I did, but I don't. But you understand that my first bond is happening right here. This is a sigma bond. A pi bond is going to be found in a double or a triple bond. I can't bond anything else in this plane. I can only bond either with the reds or with the blues. Okay? So they can't overlap end to end like this. They've got to overlap up here and down here, or they've got to overlap in the front or in the back. Well, that's a different kind of bond entirely. Okay? So this was my sigma bond, right? Now if I'm going to do it, let's say I'm going to do a pi bond, I can do one up here. Let me do this in a color. It'll help. I can do one up here, right? And now these two will share electrons in here and share electrons in here, right? Or conversely, and this is what we call a pi bond, right? Or conversely, I could do it this way. And now I could do it try to show it this way. And now I've got a bond happening here and a bond happening here. In both these cases, I understand that I've got other p orbitals here, right? I've got one that's probably coming out of my plane here. You see that tetrahedral shape happening everywhere, right? Or over here, I understand that I've got one that's going up and going down, right? But we're not bonding in those. So this would be my pi bond, right? How many bonds do I have here? Total?
3.
Mm-hmm. 1. Oh, I'm sorry. This is just, even though this looks like two different things, this is one bond.
One, just one? Okay.
Just one, yeah.
Two,
So it's
three,
2.
four.
It's 2 bonds here, okay? I got a sigma bond and 1 pi bond. So this orbital is dumbbell shaped, right? So these electrons interact at the top of this dumbbell and they interact at the bottom of this dumbbell.
Because they're like moving
Because
around.
they're, yeah. And you can't, it's the whole thing.
Can't calculate it.
You can't know exact Heisenberg uncertainty. You can't know where they're at, and you can't know their position and their velocity at the same time. You can pick one or the other. Okay, and then the same thing happens here, just in a different orbital, right? By the way, what's the difference between looking at it between this and this? It's just a matter of going like that, right? So this is a double bond, this is a double bond, but there's also triple bonds, right?
Yeah.
So for a triple bond,
Another question we had in math, other, I don't like subject. And here is,
how are y'all? You can come on in.
okay,
Just doing a little triple bonding.
chemistry too. So,
So in this one, I've got 1 sigma and 2 pi bonds.
I'm trying to remember if I remember this.
First bond is always a sigma bond. It's always in line between the nuclei, but they can't have, look at it here, so you could have a sigma, if I had another one of these just like this, you can have 1 bond here, I can't put 2 in that same spot, so they have to bond up here, or they have to bond here.
Do you remember this?
How many classes do you get, you know, crazy hard things and balloons at the same time? All right. I'm sure they're glad they came in. All right. Feel decent about that?
Yeah.
Good. If I have only 1 bond, what do I call it?
Sigma.
Sigma. If I have 2 bonds, what do I have?
E1.
Huh?
Sigma.
1 sigma and 1 pi. If I have 3 bonds,
Sigma.
1 sigma and
2 pi.
2 pi. What's the difference between a sigma and a pi bond?
Sigma theta line.
Sigma occurs between the nuclei, right? And in all the pi bonds it can't, so they have, because they can't all occupy the same space, so it's got to happen either above or, you know, below or whatever, that in one of the 2 other planes. Okay? Well, that's really good stuff. All right. What else does it want you to know? Oh yeah, let's do this. So, take a look at my bond. Again, we just got to imagine another molecule the exact same way, okay? Which bond puts the electrons closest between the two central atoms, between the 2 nuclei? The sigma bond or the pi bond?
Sigma.
The sigma does. It's right here, right? My pi bonds have to, the electrons literally have to occupy more space, right? They have to travel a greater distance. So if this whole thing of bonding is about energies and stuff like that, do I release more energy in forming a sigma bond or a pi bond?
I won't.
Sigma.
Sigma, because it's closer. Would it take more energy to break a sigma or a pi bond?
Sigma.
A sigma. So which one is stronger? A sigma or a pi?
Sigma.
A sigma. That's the conceptual stuff that that's good. That's really good thinking. So I'm going to erase this and write that for us. You know, formulas you can always memorize and do the math on, right? The conceptual stuff you either know or you don't. It's easy to want to major in the math because you can do it as long as you got the formula. But you can do the math and not understand chemistry. You can understand chemistry and not be able to do the math, but then if you just go get the thing, you know, the formula, you can always do the math. So if I spend a little extra time on this stuff that's a little more conceptual, you'll bear with me, it will have a greater payoff down the line for you. I promise. All right. So sigma bonds are stronger than pi bonds, right? In terms of strength. Sigma bonds are greater than pi bonds in terms of electron orbital overlap. Which means that pi bonds have a greater bond distance. Energy. Is that going to hold up? Let me make sure it holds up. I said this is about right. Take that back.
I think it was.
No, because there are other factors at play here. It's not as simple as I oversimplified it, and that was a mistake. All right. Simple little check, little conceptual check here. This is kind of classic homework type stuff, or test type stuff. What you want to do is you want to label every bond, and then you want to count out how many sigma and how many pi bonds. So what kind of bond is this?
Say sigma.
Sigma.
Sigma. Sigma. Sigma. Sigma and the other one pi.
One sigma, one pi, right? Good thing here. Okay, so count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sigma and 2 pi. Right? I assume that's got to be the right answer. Yeah. Okay. You want to do another one? Do one more. Yeah. How many sigma, how many pi bonds? I would draw it. I would draw it and label it.
Go.
You can expect a question like that on a test. The reason I tell you to draw it and label it is it's easy, you know, this isn't hard. It's not rocket science, so you want to do it in your head, right?
Yeah.
You miscount one thing and you miss the problem. Why miss the problem over something stupid? Label them and count them. And do it twice. Remember, if you get the same answer 2 out of 3 times, you're good. If you get 2 different answers, do it a third time. All right, how many sigma?
13,
How many pi?
6,
6.
6.
6. 1, 2, 3, 4, 5, 6. Okay. Good, 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 good. All right. Let's look at hybrid orbitals.
Hello and welcome to a video about hybrid orbitals, often called valence bond theory, developed in the 1930s by the great chemist Linus Pauling as a model of bonding to understand the three-dimensional placement of atoms in a molecule, and that is critical to our understanding of the properties that molecules have. In this video, we will look at methane, ethene, ethine, ammonia, and water as our models for hybridization. There is only a small group of atoms in the second period that the model really works for, but among those are carbon, nitrogen, and oxygen, which make up the vast majority of molecules that exist on Earth. So the model applies to a limited number of elements, but it applies by far to the majority of molecules. Let's take a look at the word hybrid. It is a blending of two varieties. If you get a horse and donkey together, you get a mule, a blending or hybrid of a horse and a donkey. Let's get to hybrid orbital, using carbon as our model. As a single atom, not bonded to anything, carbon has 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. This electron configuration is the energy arrangement of carbon's
So, real quick, what this is showing you, this is the amount of energy in, this is energy, okay? Every atom has all the orbitals, theoretically, right? But they're not going to fill them, right? Because what orbitals are electrons going to fill?
The ones?
The lowest ones. The lowest ones first. Think of why do they go around the nuclei at all? Because they're attracted, right? The closer they are, the more stable they are, right? So it'll always fill the first ones, the lowest ones first. To fill a higher one, it has to get more energy, right? And this happens when it absorbs like a photon of light, and the electron gets excited, and it goes out to some higher energy orbital, right? But then it's not stable out there. It will fall back down very quickly, and it will release that photon of light. And like this is how the northern lights work. The aurora borealis is they get excited, they hit by something from outer space, and then they go out further, but then they fall back down and release that energy as light. You can see it, and it's cool, right? Okay, but the lowest energy level orbital is the 1s. The next lowest energy is the 2s, and then the 2p, and then the 3s, right? And then the 3p, and then the 4s, and then the 3d, and they're going to fill these in order. They always want to be the lowest energy, it's the most stable. So that's all that he's saying here, but we do want to understand that for what's going on with the hybridization.
electrons. However, carbon rarely exists in nature as an individual while undergoing chemical reactions. Carbon exists with its valence electrons bonded to other atoms. When carbon
Why is he talking about the valence electrons?
Because the one that won't.
They're the only ones that can bond, right? Those low energy ones don't function in bonding. So we can kind of just ignore the 1s electrons for now.
bonds to 4 other atoms, carbon's 4 bonds are experimentally seen to be equivalent. And so when the carbon atom finds itself in a bonding situation, its bonding electrons themselves exist at equivalent energies, which requires that they hybridize to an energy that is intermediate between the 2s energy and the 2p energy.
So what did he just say? We're not worried about the 1s, right? Hydrogen, helium, we're not worried about them. But you start getting into beryllium, boron, nitrogen, carbon, oxygen, then what he's saying is, hey, when they bond, say something like carbon, it's going to make 4 bonds. It's got, we've got this orbital, and we've got these orbitals, right? 2p orbitals. Well, when they bond, we don't find like, oh, some bonds or some electrons are this energy level and the others are this energy level. What we actually find is 4 equivalent, right? So this is a hybridized energy level. It falls somewhere in between the energy of the 2p and somewhere the energy of the 2s. And this is called the 2sp hybridized level, okay? Or hybrid orbitals.
Or you can think of it as a blending or hybridization of the 2 energies, the s and p energies. And since the energies of these electrons have now changed, the shape of the orbitals they occupy are different as well, which we will see momentarily, and those are called hybrid orbitals. They are named 2sp3 hybrid orbitals. The naming often trips up students, so before we go any further, let's take a look at where the 2sp3 name comes from. The 2 comes from the second principal energy level that the valence orbitals are in. The s comes from the 2s orbital contributing to the hybridization, and the p comes contributing to the hybridization, and the 3 comes from the number of 2p orbitals used in the hybridization. Once hybridized, the 2s and 2p orbitals no longer exist, and so we have 4 2sp3 hybrid orbitals.
So what did he just say? I realize I'm going to say what he said again, but I'm going to add one little point of emphasis. So these are called 2sp3, in this case, for carbon it is. It won't be for everything, right? So the 2 comes from the principal energy level. We're dealing with this, not the first one, but the second one. The s is s. How many energy levels are in the, or how many orbitals are in the s? It's only 1, right? So we could just as easily write this as 2s superscript 1, because there's only 1. And now we're using 3 of the p orbitals, right? So we put the p and the 3, so this is the superscript, right? So the superscript tells you how many of those orbital types there are. We don't need to say 2s1, we understand that there's only 1, and then it's simply a question of, well, how many in the p are we using, okay? And we won't always use 3, as you'll see in a minute. But that's where that comes from and how to interpret it.
4 2sp3 hybrid orbitals derived from combining the energies of 1 2s orbital and 3 2p orbitals, which gives a total of 4 2sp3 orbitals. Before we look at the shape of hybrid orbitals, it would be helpful to briefly review the atomic orbitals. The 1s orbital is a sphere, the 2s orbital is a larger sphere surrounding 1s. And here we will get rid of 1s since we are only concerned with the valence electrons. Each 2s orbital is a 2-lobed shape converging at the nucleus. So there are the 3 2p orbitals. However, when hybridization occurs, the s and p orbitals cease to exist, and the 2sp3 orbitals have an entirely different shape. We can see that orbital hybridization explains the VSEPR placement of carbon's 4 valence electrons, since all 4 2sp3 orbitals are equivalent. Each 2sp3 orbital repels the others with equal force, resulting in identical bond angles. The carbon atom only hybridizes when it is in a bonding situation. Here, 4 hydrogen atoms bond to carbon by overlapping their orbitals with carbon's hybrid orbitals. So what would be the reason for this? If we go back and see that both carbon and hydrogen have unpaired electrons, the overlap allows the electrons to pair and thus go to a lower potential energy. The illustration here contains the valence electrons of both carbon and hydrogen, and since everyone likes to visualize atoms as spheres, we can do the same. Here is our carbon atom, and here are the hydrogens with the overlapping spheres, indicating the overlapping orbitals that constitute the bond. The bonds are more readily discernible in a ball and stick model, which also makes the bond angle more visible. Since all 4 sp3 orbitals are equivalent, each bonding orbital repels the others with equal force, resulting in identical bond angles. The bonds in hybridization also have their own nomenclature. The overlapping orbitals are called sigma bonds, which represents the single bond occupied by a single pair of electrons. What about double bonds? How does the hybridization model explain double bonds? We will use ethane, C2H4, to see what happens in a double bond. The single bonds we know are sigma bonds, and the double bond also has a sigma bond, but the second bond of a double bond is a pi bond. Let's see how hybridization and orbital overlap can explain a double bond. The 2 carbon atoms in ethane are equivalent, so let's look at one of the carbon atoms first. A pi bond comes from the overlap of unhybridized p orbitals, and so the atom hybridizes only 3 orbitals, leaving a p orbital unhybridized for the pi bond. The hybrid orbital is called 2sp2, the superscript 2 denoting that only 2 2p orbitals have contributed to the hybridization. The 2sp2 hybrid orbitals exist in a plane perpendicular to the unhybridized 2p orbital. Let's remove the 2p orbital for now to more easily see that. The 2p hybrid orbitals are spread out at a 120-degree angle, which means that they exist in a plane, and the plane is perpendicular to the unhybridized 2p orbital. So this is what both carbon atoms do when bonding occurs in ethane. Each carbon atom is sp2 hybridized. The sigma bond occurs with 2sp2 orbital overlap. What about the pi bond, the second bond of the double bond? Previously we said that it comes from the unhybridized p orbitals, which we see here from both carbon atoms. The top and bottom lobes of the 2p orbitals overlap above and below the axis of the sigma bond, forming a single pi bond, the space in which the now paired electrons move around. The ball and stick model shows this double bond with 2 dashes. To summarize, sigma bonds occur along the axis between nuclei. The pi bond occurs above and below the sigma axis, where the p orbital lobes have overlapped. The ethane molecule also bonds to 4 hydrogen atoms by overlapping with both carbon's other 2sp2 hybrid orbitals, creating 4 more sigma bonds. In the ball and stick model, we can readily see that each carbon has a trigonal planar geometry, and thus the whole molecule exists in a plane with the single pi bond above and below that plane. Now let's look at how hybridization can be a model for the triple bond using ethine, C2H2. The carbon-hydrogen bonds are sigma bonds, and the triple bond is 1 sigma bond and 2 pi bonds. Let's see how hybridization can accommodate this. Since pi bonds come from p orbitals, and we need 2 pi bonds, then 2 2p orbitals have to remain unhybridized, and so the remaining single 2s orbital and a single 2p orbital will hybridize to two 2sp hybrid orbitals. And there is also the violet 2px and the blue 2py orbitals. Here, each green lobe is a single orbital, and so they each have an electron, while both violet lobes constitute the single 2px orbital with a single electron, and both blue lobes constitute the single 2py orbital with a single electron. The other carbon in C2H2 also has that same triple bond, and so it has the same hybridization. Let's see what happens during bonding. sp orbitals from both carbons overlap, forming a sigma bond. The upper lobes of the blue 2p orbitals overlap, as do the lower two lobes, creating the first of the two pi bonds. Can you guess where the second of the two pi bonds comes from? Yes, that's right. It is the overlapping of the violet 2p lobes. Let's get rid of the sigma bond for a moment to take a look at something interesting. Each pi bond lies on a separate plane, and the two planes are perpendicular to each other, and so the two pi bonds are perpendicular to each other. Finally, two hydrogens will overlap with the remaining sp hybrid orbitals, creating the C2H2 molecule. The overlap of the space-filling model reflects overlapping orbitals, which is also represented by the ball and stick model. In the remainder of the video, we will look at hybridization of nitrogen and oxygen using NH3, ammonia, as our model for nitrogen hybridization, and H2O, water, for our oxygen model. In NH3, nitrogen has 3 sigma bonds and a lone pair. So how does hybridization account for this? The hybridization is 2sp3, and nitrogen has 5 valence electrons, so one of the 4 2sp3 hybrid orbitals has a pair of electrons. The 3 sigma bonds come from the sp3 orbitals with a single electron, so they can pair up, and so the remaining electron pair is a lone pair, an unbonded pair of electrons. As with sp3 hybridization in carbon, nitrogen's hybrid orbitals spread out in a tetrahedral shape. And lastly, water. Here, oxygen has 2 sigma bonds and 2 lone pairs. In water, oxygen is also 2sp3 hybridized, but with 6 valence electrons. 2 of the sp3 orbitals have paired electrons. You can probably guess that the sp3 orbitals with a single electron will overlap with hydrogen, and the remaining 2 pairs are unbonded. They are lone pairs. Again, oxygen's hybrid orbitals spread out in a tetrahedral shape. That's it for hybridization, the product of a...
Okay, real quick. I know that we're about out of time, but I want to just practice one, okay? Let's do O2. Oxygen, how many valence electrons? How many total electrons?
8.
8 total, right?
Okay.
How many valence? 6, right? How many in the first?
2.
2. Or how many in the S, I should say. Right, and then how many in the piece? 6. No.
4.
4.
Right, so 1, 2, 3, 4. Right? Okay. Now we're going to hybridize. Right? So, we're going to get O2. If I were to draw each one.
It's a double bond.
Yeah. So if I were to draw each one, right, I've got a pair of unbonded electrons, I've got a pair of unbonded electrons, I've got then I've also got to have a double bond, right?
Yeah.
So I'm going to have that. I don't like the way I drew this. It's going to be a lot easier to do it this way. and we know that these are going to share, right? So what kind of bond is this?
It's a sigma.
This is sigma. What is this?
Bond.
Pi bond, right? Okay. And then I've got unbonded electrons, and I've got unbonded electrons. Okay. Does this add up? I should have a total of 12 electrons, if this is correct, right? 2, 4, 6, 8, 10, 12. I've got one sigma bond. I've got one pi bond, okay? So, what would happen typically is we'd be looking at S's and P's hybridizing. When I have a pi bonds can only happen between p orbitals, right? So I have to have from each one of these unbonded. So this is going to form a 2 sp 1, 2, or 3.
2. Because it's double bond.
Should be a 2, right? We're not going to fool with one of these. We're going to keep one of these as a pi bond to use. We're going to use these other 2 here though, right? So when we go to do this, S, P, this way, is that correct? So I've got 1, 2, 3, 4, 5, is that correct? 1, 2, 4, 5. Does that work out? Gives me 2 pairs, 2 lone pairs, and 1 ready to form a sigma bond, right? And I've got the same thing in my other one. So my hybridization here is this, what type of a hybridization is this one? What do I call it? 2sp2, right? Same thing here, 2sp2, 2sp2, 2sp2. This one is between a 2sp2, and this is just a good old 2p. That's it. Okay. Now, the reason that hybridization matters is that for this to function this way, I can't have just a sigma and then these pi's. For this to I'm gonna stop there. We'll pick up with this next time. Okay? All right. God bless you.
Thank you, sir.
Thank you. Have a good one.